Hello, everybody. My name is Yashwant, and this is our team project for foldable robotics RAS 557. We developed a foldable quadruple robot with knuckle walking locomotion inspired by an African apes. Our teammates are Dheeraj Reddy Pashan, Tanchak Jaldi, and me, Yashwant Varaganti. So, the basic research question for the project was how can a stiffness of a robot and the materials used for the stiffness or to create a stiffness of a robot can vary the motion of a knuckle-based robot on a four-bar mechanism. So there's our website overview of the design and simulation of this bio-inspired robot. The executive summary is as follows. This project represents the design, optimization, and fabrication of a bio-inspired foldable quadruped robot with knuckle-walking locomotion characteristics, inspired by an African apes, as already told. And the adaptive gait strategies include throttling and also galloping based gait mechanisms. The table of contents are as follows. The introduction is the project overview, key design principles, how a foldable construction asymmetric actuation works. The position control is used for this is used for key design in implementation. The key objectives are as follows: developing a dynamic Mujoko model with material compliance and motor behavior, optimize asymmetric actuator signal parameters to maximize locomotion speed, fabricate physical laminate prototype using laser cut cardboard, document the complete design to fabrication workflow for educational application. Into system model identification. The main body of is made of a cardboard laminate which weighs around 4.1 gram. The dimensions are as 6350 and 5 mm for rectangular base, and there are four legs each of 4 to 5 grams with compliant joints. And the top plate is a 6 degree of freedom floating plate with a mass of 2.5 grams, and the total robot weighs around 12 grams, excluding the servo motor. We have designed the CAD design using a DXF file. This is how the leg assembly is designed, and this is how the main body design is manufactured using DXF file. Coming to the parameter identification, my teammates will be going through how they have contributed for the parameter identification, starting with Dheeraj Reddy.
So initially we have identified the servo parameters since we are using a servo in our robot for the moment. So in order to capture the servo parameters, we initially have captured a video giving PWM pulses to the motor. So we have taken this video and uploaded it into the tracker software, and we have got, got the center of rotation, and we have optimized the robot parameters using scipy.optimize. So, and then we have imported it into Mojoko, and we have done the sensitivity analysis for the servo motor. So for this experimental setup, we have connected the servo to a rigid table, and I have connected the servo to with a chapstick and measured the weight of the chapstick. So this video was captured at 30 fps. We're using a gimbal mounted to a point. And here are the results that I've got from servo parameter identification. So from this, I could conclude that the simulation trajectory shows excellent agreement with experiment data, with exhibiting both characteristic sharp shape with linear velocity ramps and round peaks. So this validates the P controller model accuracy and captures the servo's velocity behavior.
The next parameter identified was stiffness and damping identification. So the goal was to determine the stiffness characteristics of the links and overall body structure of the robot constructed using cardboard components and a four-bar leg mechanism through free vibration analysis. The methodology used for us this was using a tracker software on a cantilever beam with test vibrations. We use nonlinear least square fit to decay the sinusoidal module. Young's module identification, which is 0.77 GPa for the cardboard, was identified. We mix and matches different serial parallel combinations for link stiffness for the total system because the total robot body was is a mix and match of the continuous parallel and serial and parallel joints. The deck was modeled as a clamped beam. So after doing after doing the detailed parameter identifications, we have found out stiffness parameters as the following numbers, and for dampening parameters were also identified as dampening ratio as 0.104, natural frequency as 19.67 rats per second, and single link dampening as the given values. Now my teammate Danshuk will be going through the friction measurement parameter.
So I have measured friction measurements using a sample of foot material, then sliding the material of on our robot. So we basically took a sample material on the foot and slightly increased the angle of foot material such a way that our robot slowly falls down. And these are the values and friction parameters we calculated from the data using it.
We have done optimization results for four test cases, and these are the following performance metric comparisons. Uh, over the different cases over the different test parameters used, we have identified that the test case 2 has an average speed of 0.0182 to 0.0812, and the maximum speed comparison is also greater for case 2, that is test 2. The horizontal displacement, that is the two and the robot's displacement between the 2 points is greater for test 2, and this the average and maximum speed comparison is also greater for test 2. So the parameters used for different tests are the angle differences for the servos, which helped us to track the desired results. So as you can see, these are the best configuration and best displacement for the given robot, for a robot. And so coming to after detail analyzing all the test cases and all the time, displacement, average velocity concluded from the four tests, we conclude that test case 2 gives the best result for the required optimized. Now I'll be taking you to the robot motion video. So this is how we have recorded the robot motion. As you can see, we are able to see the throttling mechanism and a small deviation in the joint over the first two joints at the front two legs. Now going forward for the CAD design, a teammate Danshuk took over the CAD design, and he has shown how a 4-bar mechanism can be used, and we can also see there is a place for joints where the robot goes back up and comes over on its hind legs. Going forward, my teammate Dheeraj will be explaining you how he has done the Mojoko simulation, and he will be showing you a video for Mojoko simulation. Dheeraj, over to you.
Hello everyone, here is our Mojoko simulation. So initially, since we have started the design in CAD on shape, so we used that as reference for the parameter lens and the links and everything. And then we have written the XML code and then deployed into Mojoko and continuously verifying it so that we could get the appropriate model with appropriate links, just like we have done in the hardware. So just like we have done in the hardware, we have used only one actuator that is connected to part 1, and whenever we try to move the actuator, we could be see that robot is able to get the motion. So this is the demonstration of how the robot is moving in our simulation.
So this is how we have designed, manufactured, ideated the robot which is based on 4-bar and has multiple gate motions with a focus on throttling gate. I'm sorry. We would especially like to thank Professor August for his valuable feedback and on his guidance for this project. and helping us ideate the design, manufacture the design, help us optimize the design. We would like to conclude the presentation. Thank you.